Most people think sleeve gastrectomy works because the stomach gets smaller. Less room means less food, so the number on the scale goes down. That sounds logical. It is also incomplete, because after this operation, many people do not simply feel full after a smaller meal. Their hunger can feel different. Their response to food can change. Blood sugar may improve surprisingly quickly. Something has changed in the conversation between the gut and the brain. To understand the twist, start with the operation itself. In a sleeve gastrectomy, a surgeon removes a large curved portion of the stomach and leaves a narrow banana-shaped tube. The intestine is not bypassed. Food still follows the usual route. The new stomach holds less, and that physical restriction matters. But the removed tissue was not an empty storage pouch. It was living, signaling tissue. The sleeve also has an unusual origin story. It began as the stomach-reducing first stage of a more complicated operation called a duodenal switch. For patients at especially high surgical risk, doing the procedure in stages could make the first operation shorter. Surgeons expected to return later for the intestinal part. Then they noticed something important. Some patients lost substantial weight after the sleeve alone. The supposed first chapter was powerful enough to become its own book. That discovery forced a better question. If the intestine had not been rerouted, why was the sleeve doing more than simply blocking large meals? One clue was ghrelin, often called a hunger hormone. Ghrelin is produced in several places, but a major source is the upper part of the stomach, especially the fundus. Much of that area is removed during a sleeve. After surgery, ghrelin levels often fall, particularly early on. For some people, the constant biological megaphone saying "find food" becomes quieter. That does not mean ghrelin disappears, or that every person has the same response. Hunger is controlled by many signals. Still, removing ghrelin-producing tissue helps explain why a smaller meal may feel easier to tolerate than the old container explanation predicts. Then there is the other side of appetite. Signals that say a meal has arrived. After sleeve surgery, food may leave the stomach and reach the small intestine more quickly. Cells in the intestine sense those nutrients and release messenger hormones, including GLP-1 and PYY. After meals, these signals can rise more strongly than before surgery. GLP-1 helps the pancreas release insulin when glucose is present, slows some aspects of digestion, and communicates satiety to the brain. PYY also contributes to the feeling that a meal is complete. Picture tiny messengers leaving the intestine, checking in with the pancreas, and sending updates upstairs. The stomach is smaller, yes, but the body's notification system has also changed. This is the gut-brain axis, a busy network linking the stomach, intestine, pancreas, nerves, hormones, and brain. It is not one wire and not one master switch. Nutrient sensing, the vagus nerve, bile acids, insulin, ghrelin, GLP-1, PYY, and other signals all contribute. Researchers still debate how much each pathway matters. The honest answer is a team, not a superhero hormone. That team helps explain why metabolic changes can appear before a person has lost all the weight they eventually will. Better glucose control is partly related to weight loss, but altered meal size, nutrient flow, insulin sensitivity, and gut hormones can also contribute. This is why the modern term is often metabolic and bariatric surgery. The operation changes anatomy, but its effects travel through physiology. For decades, obesity was often described in painfully simple language. Eat less, move more, try harder. Energy balance matters, but that slogan ignores the systems that influence hunger, satiety, food reward, and how strongly the body defends its weight. Sleeve research became part of a much larger scientific shift. Appetite was no longer just a personality test. It was measurable biology. That same shift helps explain today's anti-obesity medications. Drugs such as semaglutide act through GLP-1 receptors. Tirzepatide acts through GLP-1 and GIP pathways. They do not copy sleeve surgery, and surgery did not invent these medicines. Rather, bariatric research and drug research converged on the same big idea. Gut-brain signals can powerfully change appetite and metabolism. There is a historical echo here. Some GLP-1 medicines were first developed and used for type 2 diabetes, where their effects on glucose regulation mattered most. Their effects on appetite and weight then became impossible to ignore, leading to medications specifically approved for chronic weight management. The path went from glucose control to a broader understanding of obesity biology. But neither route is magic. GLP-1 based medications commonly cause gastrointestinal side effects, especially while the dose is increasing. Nausea, vomiting, diarrhea, constipation, and abdominal discomfort can occur. Persistent vomiting or diarrhea can lead to dehydration. Product labels also include warnings about less common serious problems. So these medicines belong in medical care, not in a casual online experiment. Sleeve gastrectomy has its own trade-offs. It is irreversible surgery. Early risks include bleeding, a leak along the staple line, infection, blood clots, and complications of anesthesia. Later, some people develop or worsen acid reflux, narrowing, vomiting, food intolerance, gallstones, and nutritional deficiencies can occur. Vitamins, laboratory checks, and long-term follow-up are part of the treatment, not optional decoration. And then there is the subject that deserves more compassion than it usually gets: weight regain. Some people regain part of the weight after surgery. Some regain after stopping an effective medication. That does not prove they became lazy or that treatment was fake. Obesity is a chronic, relapsing disease, and biology adapts. Appetite signals can shift again. The stomach can change over time. Sleep, stress, illness, medicines, mobility, mental health, food environment, and eating patterns can all influence the result. The original operation still happened, but the system around it keeps moving. A treatment that changes biology at year 1 may need support at year 5. That is also why some patients use anti-obesity medication after bariatric surgery. A clinician may consider medication when weight loss is insufficient, when weight returns, or when related health goals need more support. This is not surgery versus medicine in a dramatic winner-takes-all contest. Sometimes they are different tools used at different points in the same long-term plan. None of this means sleeve gastrectomy is right for everyone, or that a particular medication is the answer for every patient. Decisions depend on health history, goals, risks, access, and careful evaluation. This video is an explanation of the biology, not personal medical advice. So return to the familiar picture. A large stomach becomes a smaller sleeve. That picture is true, but it is only the outline. Inside it is a quieter hunger signal, faster nutrient delivery, stronger post-meal messages, pancreatic support, brain responses, and a body trying to establish a new balance. The most important lesson is not that willpower is irrelevant. It is that willpower operates inside biology. Sleeve gastrectomy became a standalone procedure because surgeons saw results that stomach size alone could not fully explain. Modern medications reinforce the same idea from another direction. Obesity treatment works best when it respects the signals, the side effects, the limits, and the need for care over time. A smaller stomach is the visible change. The hidden change is the conversation. Gut to brain, brain to behavior, pancreas to blood sugar, hormones to hunger. And once you see that network, sleeve gastrectomy stops looking like a simple container trick. It becomes a lesson in how deeply the body talks to itself.